we're talking about an interaction where the effects of duration are different for single tones than for paired tones. And this is a great example of that because for paired tones, there doesn't look like there is an effect of stimulus duration. As you go from 6 to 20 to 50 to 100 milliseconds in duration, in the paired tones, there's no effect of duration. We already said that the main effect of duration was that as you increase the duration, the response probability increased, but turns out that's only true for the single tones. So that's what an interaction is. When you have an effect of one factor, duration, that's different at different levels of the other factor. And the nature, when I say, what's the nature of the interaction, you need to tell me how it's different. Well, here's how it's different. Stimulus duration increases response probability, right? The longer the duration, the greater the probability you'll respond. But that only happens for single stimuli. There is no effect of duration for paired stimuli, and that's the nature of the interaction. Stimulus duration increases response probability, so response probability increases with increasing stimulus duration, but only for the single tones. Let's take a look at another study. So we're interested in the effects of sleep on air traffic controller performance. It's very important for them to get sleep so they'll do a good job. This is a study that was done to demonstrate just that. So here we're going to measure the number of radar targets they can correctly identify. We're going to manipulate two independent variables at the same time, so two factors in this study. The first one, we're going to use different people in different groups, right? So we're just going to ask people to stay up for different amounts of time. So one, we're going to get them right after they woke up, 2 hours after they woke up, that is. Another, we're going to look at later in the day. So they've been awake for 12 hours already. And a third group of people, different people, we're going to ask them to stay up all night, and then we're going to test them. Of course, these aren't real radar targets. This is just a simulation, so everybody's safe. So there's three levels of the first factor, and this is important. The first factor is a between groups variable. The second factor, the second independent variable, is session. So air traffic controllers don't show up to work and just work continuously from 9 to 5 and then go home. They take breaks. And so the other question that we're asking here is not just how much is sleep important for correctly identifying radar targets, but how many sessions can you do? So is there effect of doing one session, then a second session, then a third? We're going to have 4 different sessions, but this factor, you'll notice, is a repeated measures factor. So it's a within subject variable. When you have two different factors being manipulated in this way, one is a between groups variable and another is a within subjects variable, you call it a mixed design. So what we're mixing here, we would call this a 3x4 mixed factorial design. And what's mixed is that one is a within subjects and one is a between subjects factor. Okay. So this might be how we would record our data on this sheet here. We have 3 different groups of different people, right? Subjects 1 through 4, and getting 2 hours, just 2 hours after they woke up. It's not 2 hours of sleep. They've only been awake for 2 hours. Another group of 4 different people who have been awake for 12 hours, and a third group of 4 different people, still different, who have been awake for 24 hours. Each person does 4 sessions, right? And that's our repeated measures factor. So again, this is a 3 by 1, 2, 3, 4 sessions mixed factorial design. Here's what the source table might look like, right? So remember, in a source table, you're going to get sums of squares for these different sources of variability. Hours without sleep, right? The within treatments sums of squares, which you'll need to get the within treatments mean square. That's going to go in the denominator, but only for this hours without sleep variable, because that is the between groups factor. Now remember, the source here is within treatments sums of squares, and we use the mean square for that. we divide that into this mean square for the hours without sleep variable. We have session number, which is the repeated measures factor, which means we're going to use MS error, right? MS error for the denominator. And there it is right there. This is MS error for this session. Remember, that's going to be much smaller than MS within because we subtracted out that variability due to subjects. And of course we have the interaction sums of squares listed here. So there's 3 different F's. We have an F for the main effect of how long has it been since you slept, an F for the main effect of session, and an F for the interaction between these two. All 3 of these are significant. Let's check out how that worked in this graph. So here we have the shorthand lines again. These are lines connecting the means for each of the 4 groups in each of the 3, let me try that again. These are lines connecting means from each of the 4 sessions, right, over each of the 3 hours without sleep groups. All right. I already told you both main effects and the interaction were significant. Let's take a stab at describing the nature of the main effects and the interactions. Let's start with hours without sleep. To do this, you have to look at sort of the whole line A1 versus the whole line A2 versus the whole line A3. What is happening as you go from 2 to 12 to 24 hours without sleep? What's happening to the dependent variable? Well, overall, if you average across session type, right, if you look at the midpoint of the line here, moving down to here, moving down to here, well, it looks like they're detecting fewer targets. So the longer it's been since you've slept, the fewer targets you detect successfully. That makes sense, right? You stay up later, you don't do as good a job. Okay, that's the main effect of this between groups factor. What's happening on average as we move from the first session to the second session to the third session to the fourth session if we average across these 3 groups of the other factor? So what's the main effect of the repeated measures factor, the session? Well, the average of these 3 points is closer to the 2, so it's like right around here. Kind of the same place for session number 2, but as we move down, and again, I'm looking for the average of these 3 points right here along these lines. It's somewhere around here. And the average of these 3 points is somewhere down here, right? So if you average across hours without sleep, it looks like the more sessions that you do, the fewer targets you detect correctly. And that makes sense too. So the longer you've been at work, regardless of how much sleep that you've had, the fewer targets that you'll detect successfully. Okay, so that's the main effect of the within groups factor, right? The repeated measure, which is how many sessions did you do? Each person participated in all 4 sessions. Now let's take a look at the interaction. You have an interaction when the effects of one factor, let's say session, are different at different levels of the other factor, which in this case is the between groups factor, the hours it's been since you've slept. And I already told you the interaction was significant. What's the nature of that interaction? How are the effects of session different as we get less and less sleep? Well, it looks like session doesn't really affect mean number of targets detected in the 2-hour group at all. So there's no effect of session here because it's pretty flat. But when you've been up for 12 hours, then session does start to have an effect that is even more pronounced if you've been awake for 24 hours. So the effect of session increases, right, from nothing to something worse. The effect of session is greater the longer it's been since you've slept. And that actually makes sense, right? These 2 things combine to work against you detecting targets correctly. One final example comes from Halpern and Bower's paper in 1982, and this is looking at musical expertise and being able to reproduce musical notation from memory. So if I let you stare at this for a while and memorize where these notes are, you might be able to copy this over onto a piece of paper. If you've had musical training, then you probably recognize that this first melody in line A actually follows the rules of music theory, and it sounds pretty good. B, if you would play this out on the piano, sounds actually quite bad. It doesn't sound good. So A sounds good, B sounds bad, C is totally random, and it may or may not sound good or bad. But we wanted to see whether the melody quality affects your memory for the musical notation. Of course, you might think that people with musical training would do better at this, so we're going to look at that as a factor as well. All right, so these are the results from the study. We're looking at data from musicians in M and non-musicians in M for good, bad, and random melodies. Okay, so we played musicians the good melody and non-musicians good melody, and we're measuring how similar what they drew on a blank piece of paper was to what we showed them originally. Obviously, as a main effect, musicians are going to be better at this than non-musicians. So that's an easy main effect to identify here. So averaging across good, bad, and random, right? The main effect of whether someone's a musician or not is pretty easy. Musicians are significantly better than non-musicians. And on average, right, if you average musicians and non-musician scores together, it's easier to recall a good melody than a bad melody, and random melodies are the least easy to reproduce correctly because you get less and less similar to the original as we move from good to bad to random. But that main effect of melody type really is explained better by the interaction between musical expertise, whether you're a musician or not, and melody type. So if you look at just non-musicians, there really isn't much of an effect of melody type. Yeah, maybe a random melody is kind of harder to reproduce, but the effect of melody type is much more pronounced for musicians. So melody type influences musicians' mean similarity score greater than it does that of non-musicians. And that's the nature of the interaction. Interestingly, if you look in the report here of the results, all of these were significantly. Both main effects were significant, and the interaction was significant as well. And now you guys know how to interpret those main effects and interactions just from looking at this graph of the two groups, musicians and not, by 3 melody types, Factorial Design. One last thing. Throw you a little curveball here. You remember the Martini study? It's a 2x2 Factorial Design, 2 levels of drink type, 2 levels of audience size. We tried connecting, the bars to use our line shorthand. Imagine that we did this as a imagine that we added a third factor here, right? Men and women. So we're going to look at gender. We're going to look at audience size, drink type, and gender. So each one of those factors now has 2 levels. So it would be a 2 by 2 by 2 Factorial Design. And you'd end up with 7 different values for F. You'd have an F for the main effect of drink type, an F for the main effect of audience size, a third F for the main effect of gender or sex, 3 two-way interactions. You'd have a 4th F, this one testing for the interaction between drink and audience, this one testing for the interaction between drink and sex, this one testing for the interaction between audience and sex, and you would have the possibility of a 3-way interaction. So a significant 3-way interaction means that there's a 2-way interaction that's different at one level of the third factor than it is at some other level of the third factor. I know that's very confusing, but let me show you what that might look like. Okay. For men, the data may have worked out like this. The Martini decreases your anxiety, but only in front of a small audience. It's not enough to do that in front of a large audience. And for women, it might have worked out differently, that the Martini actually increases their anxiety in front of a small audience. Drinking the placebo, actually women didn't have a problem speaking in front of a small audience without any alcohol at all, but the alcohol increased the number of errors. It might have worked out this way. And if it did, it means that the two-way interaction that's so very obvious here for the men, why is there a two-way interaction? It's because the effect of the martini is different in front of a small audience than in front of a large audience. So the effect of this drink type factor is present only in front of a small audience. Well, here that effect is opposite in women. So you have a two-way interaction that's different at one level of a third factor than it is at another level of a third factor. And if that didn't confuse you, then let me show you one more thing. This is the number of F's that you have if you have a four-way analysis of variance. So you'd have four main effect F's, 1, 2, 3, 4, 5, 6 two-way interaction F's, 1, 2, 3, 4 possible three-way interactions, and of course the four-way interaction. And this is one of the reasons that people don't really do this type of analysis, is because if you were, if you got a significant four-way interaction here, it might mean something like martinis reduce the number of errors you make, but only in front of a small audience, and only when you're a man who is under 45 years old. And, it gets very difficult to interpret. Alright, that's it for today's video lecture, and I will see you next time.